In the previous lecture, we did stop at critical thickness of insulation. So today we're going to discuss about a new method for determining. So somebody again is trying to enter. So I hate this thing. Yes, so we did discuss about thermal resistance, okay, in cylindrical, spherical, and then rectangular axis. So this particular method is slightly different from those methods that we have discussed so far in relation to heat transfer. So the concept of numerical method is the adoption of finite difference method. Okay, so ideally it is based on differentiation. Okay, so we're going to consider heat transfer in two-dimensional coordinates in solid surface. Okay, so where we are going to adopt the idea of numerical methods or finite difference method. Okay, so let's consider we have a flat plate of this dimension. And on this flat plate, we have what do you call it? A certain grid. Okay, so grid distribution means that we have divided it into different portions. Okay, in the x coordinate and y coordinates, and we take equal distance of along the y-axis and then the x-axis, as you can see on the slide. Okay, so then we denote each particular point. Okay, between each particular point, we have what we call a node. This is what we call a node. And then this is also another node. So this node are the nodes in the x-axis, and then the nodes along the y-axis corresponds to this. So the distance between this node is given by delta y. The distance between each node along the x-axis also, let's say it is delta x. Okay, so, and then let the thickness of the flat plate or whatever object it is be b. Okay, so now we want to take a particular node as a reference. Okay, for example, we take this if we take this particular node and then we consider that there is some amount of heat transfer from its neighboring node towards this central node. You understand? So there is heat transfer from different directions along the x-axis, along the y-axis, towards the central node. Okay, so then we'll say let the magnitude of the heat transfer from each particular node, let's say along the x-axis and on the y-axis, be equal to, let's say, if you are moving from this particular direction towards the left side, then we move a distance about m. So the coordinate of this, the central node. So again, somebody is trying to enter the class. So please try as much as possible to enter the class early so that we don't interrupt with our lectures, okay? Yes, so like I was saying here, we have a central node. Okay, so this is our central node, and the coordinate of this node is m. Okay, so that's the x coordinate, and then the y coordinate is given by this. Okay, so if we move to the right of this particular node, it means we move m plus 1, magnitude of 1. Okay, but the n remains the same because we are not moving in the y direction. We only move in the x direction by a unit of 1. Similarly, if we consider the left-hand side, okay, so we want to observe the heat transfer from the left-hand side. So if we move to the left of m, then it is decreased by 1, magnitude of 1. Okay, but again, the magnitude and the y-axis remain the same, doesn't change because we are not moving in the y direction. Okay, so similarly, along the, let's say, the top node. So the heat transfer towards this central node is given by this particular magnitude. Okay, so the m and then the n are just the coordinate, the reference coordinates with respect to each particular heat transfer. Okay, so now let us come to our concept of differentiation. You see, we all know in differentiation, or let's say if you have a differential equation, okay, delta f, okay, divided by delta x. Okay, so it means the differential of a function f with respect to x. This equals to the limit as delta x approaches 0. Okay, so then it is going to give us fx plus the x minus f of x divided by dx. Now, if you look into this diagram, this gives us the picture about this particular equation. Again, somebody is trying to enter the class. So, okay, so let's proceed. Yes, so if we look at this particular graph, okay, let's say we have a line, the green line, and then we locate 2 points on the line. Now, if you want to find the gradient of this line, it is the gradient of the line. So who is that disturbing again? So, and when I was sending the WhatsApp, they didn't see or what. So enter the class early. So then you stop disturbing us. Okay. Yes, so like I was saying, if you want to find the gradient of this line, it is simply the vertical distance, okay, divided by the horizontal distance. Okay, so vertical distance with respect to this f of x and f of x plus and the x, that's the difference between this function. So we locate a point. Let this point be f of x on this axis, and then it is being displaced by the function df. That corresponds to f of x plus dx. So this is the vertical distance. So that vertical distance is what we have over here. Okay, so f of x plus dx minus f of x divided by delta x divided by, and then we have delta, the difference between x plus delta s minus x. So that gives us again delta x. Okay, so if we find the limit, in the limit as delta x approaches 0, this delta x approaches 0, then the partial derivative of this particular function is approximately equals to f of x plus dx minus f of x divided by delta x. Okay, so you may not understand the implication of this equation now, but you have to be a little bit patient. Okay, so now we look into, again, a different concept. Okay, so we are still considering this particular line as our line, and then we want to define or determine the gradient of this line. This time around, we locate a point at the middle portion, and we denote the magnitude of that point, or the coordinate of that point, to be m. Similarly, the temperature that corresponds to this particular point is given by Tm. Okay, so now if I move to the right of m by a unit of 1, so then it means this portion will be m plus 1. And if I move to the left of m by a magnitude of 1, so that gives me m minus 1. Okay, so but half of this portion, half of this distance is m minus half. Similarly, half of this is given by m plus half. You understand? So that's the what we call the explanation for this particular horizontal portion. And then for the vertical portion, we have, like I've told you, we duplicate a point Tm. So if we move down, okay, to the by a distance of -1 from m, then that gives us Tm minus 1. And then the same thing applies to this. Okay, so what we did over here is that we divided the distance L, okay, into different portions of m. Okay, so different portions of m is being divided. So different portions, L is being divided into different portions. Let's say m, we have here m and plus half, then m plus 1, and so on like that. So now the differential, yes. So if we go back to this particular fundamental equation, if we differentiate this function, we get f of x dx minus f of x divided by delta x. So we are applying the same concept over here. Let's say if I want to find the derivative of this function, dt over dx, okay, at the point m minus 1, it is simply given by Tm, which is this point, minus Tm minus 1 divided by delta x. So think of this magnitude to be the vertical distance that I have discussed with you already. Okay, so we want to find the gradient of a line, okay, with respect to this particular function. So this is the vertical distance is this, and then the horizontal distance. So again, we locate 2 points like this, where again the middle portion is m minus half. Okay, so the vertical axis, sorry, let me draw it carefully. Yes, so we have, this is the temperature axis, and this is the x coordinate axis. Okay, so if you want to find the gradient of this line with respect to the, think about this one to be the vertical distance, which we have divided. So it is the vertical distance divided by the horizontal distance. So the horizontal distance is simply delta x. Okay, so similarly, if we want to find the gradient, so the the differential of dt over the x in the neighborhood of m plus half, in the neighborhood of m plus half, we are talking about this load, neighborhood of this. So that gives me Tm plus 1 minus Tm divided by, again, delta x. You understand? So now, if we want to find the double derivative, we want to differentiate this function again with respect to x. So it's going to give us the squared, the t square over the x, sorry, the square t over the x square. Okay, so then it means we are going to differentiate this again one more time. So eventually that gives us this equation. See? So if we differentiate this function again with respect to x, so that's the square t over the x square. So it implies that we are going to differentiate this particular function again, and its differential is simply the derivative of this. So we are taking this point minus this particular point divided by delta x. So now eventually, if you substitute, we know dt over the x, okay, in the neighborhood of m plus half, and then dt over the x in the neighborhood of m minus 1. That gives us these two functions. So if you add these two, subtract these two functions, one from the other, so eventually we'll have an equation like this. So now, the square x is just the same. So, and delta s becomes, so sorry, I'm very sorry. If you add this, sorry, subtract this function from this, so we're going to have a function in term divided by the x. So this, the x will come to the denominator part, and then it will be the x squared. Okay, so from now, another way in which we can develop this function. So the same thing, the square t over the y square is also given by tn plus 1 minus 2 tn plus again tn minus 1 divided by delta y square. So, and if we have similar function like this, let's say we have a three-dimensional and a plane wall. We want to determine the rate of heat transfer or the temperature distribution along the surface of that particular plane wall. Okay, if it is one-dimensional coordinate system, then it means that we all know that for a rectangular surface, there we have what do you call it? The partial derivative of the T over the the T, which is the temperature term, should be equal to the square T over the S square plus the square T over the Y square, and then that of the Z term as well, plus heat generation, if there is heat generation. Okay, so that was the old equation that we know about. But now we know how to replace this function using the finite difference method. Okay, so now instead of integrating this particular function to get the value for t in terms of x, we are going to instead substitute using this particular equation. You understand? So now the differential of this is the same as this particular equation. So now we have the heat generation part is given by this, which is not equal to 0. So now you rearrange this equation. So again, we say where Q is the rate of heat generation per unit volume at the node. Okay, so now, again, if we have a situation where we have, let's say, a two-dimensional system. Two-dimension means that when only the z part equals to 0. So this is a steady state condition. Again, we are going to make a substitution for this square, the square t over the s square, make a substitution for the square t over the y square, which is nothing. It corresponds to this and that equation. You understand? And then the q divided by k becomes equals to, it becomes a minus in this way. Okay, so the solution to this particular partial differential equation is governed by this particular equation. So later I will show you a very simple method by which we can handle this. Okay, so now the diagram that we have over here is similar to what I've discussed previously. We consider a central, this is what we call a central node with a magnitude coordinate of m and n. M is the s component, and then n is the y component of this particular node. Now, if we move to the right of this node, we move m plus 1, then comma n. And then if we move above this node, it means we are moving along a distance in the y direction. So we have m, okay, comma n plus 1. So the same thing applies to if we move to the left of the node and then move downwards. So, and this is what we call a central node. And then the neighboring nodes are these particular ones. Okay. So now, yes, so I'm very sorry. Let's see over here. In relation to this particular equation, so we have heat transfer in two-dimensional coordinates, namely in the x direction as well as the y direction. So it means that this particular diagram satisfies this particular equation. And this Q is the heat generation at this particular node. You understand me? So fundamentally, the temperature distribution with respect to this particular node is given by this equation. Okay. So now, if we assume that delta x equals to delta y, so now there will be a common denominator on both sides. Okay, so here we have if you assume that delta x square is the same as delta y square, then it simply means that we can add the denominator part, and then we can multiply the delta y, delta x by this particular function. So eventually, this is what we have over here. Okay. So we allow delta t, and eventually, if we say delta x equals to delta y, then the numerator portion of the previous equation becomes t m plus 1 n, and then t m minus 1 n, then t m n plus 1, and so on and so forth, and then minus 4 t m n, all should be equal to minus q m n delta x squared divided by k. You understand? So here, now, if we come back, so we say since we are considering that k is constant, then the flows, okay, the flows may all be expressed in terms of temperature difference, and then the same equation can be derived. So now let us come to the Fourier's equation, Fourier's law of heat transfer. As far as Fourier's law is concerned, it states that Q equals to minus Ka delta T divided by delta X, where again, yes, so the area across which the heat is being transferred is given by delta Y times 1. Okay, so delta Y times 1 means that the 1 is the thickness. So let me explain over here. So you see, if we have a grid, something like a grid like this. This is a central node, okay? And then we have neighboring node, okay? So let's say neighboring node 1, 2, 3, okay, 4. These are the neighboring nodes. Now, let me write this properly. Yes, this neighboring node 2. If we want to consider the heat transfer from this node 1 towards the central node, it is going to be minus k a dt over dx. Now the area, the area means that this, and the area simply tells us that, you see, this particular y-axis, oh sorry, I'm very sorry. So we divide this portion into 2 and divide this portion also into 2. And this accounts for a magnitude of delta y. So delta y times the thickness. So thickness means if we have a plane like this, so it's very difficult to for us to imagine what I'm trying to say. Yes, we have a plane like this. We have a plane like this. And you can imagine that there is heat transfer towards this particular plane. Okay, so now and the vertical, this distance is given by this. Okay, and that's the y component. That's the delta y. And then, oh, sorry, and yes, that's the delta y component. And then the magnitude of 1, that's the thickness across which the heat is being transferred is this particular one. So it is going to give us the area is going to give us this particular height times oh, I'm very sorry. So it should be this instead. So we have this particular distance times that. So that gives us the total surface area of this particular surface where it is receiving the heat. So it is, again, this one, again, is the thickness. So that I've explained to you over here. If you can see this diagram, yes, so the B over here corresponds to 1. Okay, so then we have delta y in this direction and then delta x in this direction. So if I want to find the surface area across which the heat is being transferred, okay, onto this surface. So the heat is transferred onto this surface, for example. Then it is going to give me this particular distance times the thickness. Yes, I think this is more clear. So times the thickness. So the thickness is this. Okay, so that gives us the 1. Now, let us move ahead. So I'll finish these slides quickly, and then that will be the end of the lecture for today. Okay, so now if we consider these particular equations, we have Q, the heat transfer, rate of heat transfer from the left, okay, by conduction is nothing equals to Q m minus 1. We move a distance of m minus 1 and n. This should be equal to K times delta y, okay, then Tmn minus Tmn divided by delta x. Okay, so again, if you move to the right, so consider the conduction from the right. It is given by K delta y. Okay, then we have Tm plus 1, and then n Tn m minus n divided by delta x. So the same thing applies to this particular component in the upper portion and down portion of the node. So eventually, if we add all the heat transfer along each particular node, we have this Q, this Q, this Q, this Q, plus the heat generation times the area. This should give us this particular function. Okay, so sometimes we'll cancel out and the temperature at the center is given by T. The temperature of this portion is T m height of this node. Okay, let's say I have node 1, node 2, node 3. Okay, node 3 is this, and then node 4. Okay, so with respect to the okay, across this particular node, you see it moves T, this portion becomes Tm plus 1, a magnitude of 1, and then comma n. You understand me? So it is this temperature over here plus the temperature at the left side. So Tm minus 1. So it's very easy to follow this, and then dash n. Similarly, plus the temperature m, and then dash, sorry, comma n plus 1. So it means we are moving 1 magnitude in the y direction, and that is this temperature. This temperature corresponds to this. And then the final one, the temperature that corresponds to this, is there for this particular portion. So it is this particular yellow. Can you hear me?
Hello, sir.
Yes.
Can you please repeat from the TM from the beginning, because we lagged for a moment about 2 minutes ago.
Oh, okay. Sorry. You mean I should go back?
No,
Where?
no. This one. Yes, this one.
This particular one.
Yes.
Okay. So let me explain again. So what I'm saying is that maybe let me erase everything. Let me erase everything. Sorry, ne? So you don't need to memorize this equation. It will come naturally. By the time I will start solving questions, then things will become very clear to you. So what I mean over here is that, let's say we have a plain wall, okay, and we divide it into this portion. So the temperature over here at this node is given by Tm minus n. Sorry, Tm minus 1, comma n. That's the temperature at this portion. This for number 1. And the temperature at the top. So this is a central node. It's a central node. So this node number 2. Node number 2 means we are moving in the y direction. 1 magnitude of 1 in the y direction. Okay, so it means that we will have Tm. So x, it remains the same. X does not change. So it is this particular temperature at this portion. Similarly, if we move to, let's say, node 3, it means we are moving to the right of this node by a magnitude of 1. Okay, so it means that we will add m. So this is going to be Tm plus 1, m plus 1, m plus 1. So m plus 1, comma, n. Because we are not moving in the y direction, so n remains the same. Similarly, at the bottom part, it means that, yes, oh, sorry. So for this particular one, the temperature over here corresponds to Tmn. Okay, so the temperature is Tmn. So if we move downwards, then the temperature over here is going to be Tm, comma, n minus 1 in this way. All right. So then the temperature that corresponds to the left portion is this. Okay. So if you want to find, this is what we call a central node. Central node. For all central node, if you want to find the temperature distribution of the central node, it is the temperature to the right of the central node plus the temperature to the left of the central node plus the temperature at the top of the central node plus the temperature at the bottom of the central node minus 4, this 4, times the temperature at the center of the node. Okay, so in future, let's say, sorry, if you have a distribution like this, where the temperature over here, let's say, equals to 10, the temperature over here equals to 5, the temperature over here equals to, let's say, 7, the temperature over here equals to 8, and then let's say the temperature over here equals to 2 at the middle portion. So if you want to find the, let's say, the temperature distribution with respect to this node, it is going to be the temperature to the right of this node, which is 7 plus 10 plus 5 plus 8 minus 4 times 2. And this should be equal to this particular function. It should be equal to minus Q. If you know the value for Q, then you put the value for Q. If you know K, you put the value for K. Then if you know, let's say, so for all cases, maybe the temperature at this portion may not be given. Yes, so maybe let's delete this. Let's say this one is T. Maybe you want to determine this temperature. So they ask to determine this temperature. Then it's going to be T plus 5 plus 7 plus 8 minus 4 times 2. Then this should be equal to minus Qm, okay, the m comma n times delta S squared divided by K. You understand me? So this is how to handle this particular situation. So we were going to look at an example over here. So for this particular example, let me see over here. Yes. So we have a solid surface in which the temperature on this portion, on this surface is 500, temperature on the other side is 100 degrees Celsius. So temperature at the bottom is 100, temperature on the other surface, this portion is also 100 degrees. So compute the temperature at various nodes and then the heat flow at the boundaries. So what we will do is that now we want to use the finite difference modeling method. Okay, so the magnitude or the dimension of the plate is given by 1 meter squared. Okay, then the value for K is given, and then the temperature across the surfaces. So what we're going to do is that we will distribute the temperatures into what we call nodes. Okay, so this is node 1, node 2, node 3, and then node 4. And again, we consider the whole surface, you see, if you look at this particular surface, the temperature across the surface of this geometry is what we have over here. Okay, so that's the temperature. So we have 100 here at the top, we have 500, we have 100, again 100 at the bottom. Okay, so we divide it into so many different nodes. Okay, so you are not supposed to worry about the division of the nodes now. Later on, I'll show you how to do the division. Okay, so we have a node 1. Let's consider first node 1. At node 1, also what we are going to do is that the neighboring node for node 1 corresponds to node 2. That is at the right-hand side. So somebody want to enter the class again. So what happened to you? Yes, so let's proceed. Yes, so what I'm saying over here is that the neighboring nodes that corresponds to node 1 is node 2, node 3, and then the temperature T 500, T equals to 500. And then also the temperature T equals to 100 to the left of it. Okay, so these are the neighboring nodes that, that corresponds to node 1. Okay, those are the neighboring nodes. We only take the nodes that corresponds to this central node from the right, from the left, from the top, and then from the down part. So we don't consider node 4. Node 4 is not a neighboring node to node 1. You understand? So, and again, we are going to assume that the magnitude of the distance between each node is given by, let's say, 1/3 m. Okay, in the x component is this, in the y component is also this. Okay, so now if we add this 1/3 plus this 1/3 plus this 1/3, that gives us 1. You understand? So that gives us 1. So now, if we look carefully, if we consider node 1, for node 1, how is going to be the temperature distribution? It is going to be the temperature T2. You see, node 1 is this. It is going to be T2 plus 100. So the temperature to the left of node 1 is 100 degrees Celsius. That's it. And then the temperature at the top of node 1 is 500, which is this one. And then the temperature to the bottom of node 1 again is T3 minus 4T1. Okay, should be equal to 0. This equals to 0 because there is no heat generation. If there were to be heat generation, then you have minus Q divided by K times delta X. So, but all those things are equal to 0. Now, if you consider node 2, in node 2, the neighboring node to node 2 is node 1 to the left, and then this particular node whose temperature is 500, the temperature on all these surfaces is 500. And then also, the temperature over here is 500. And then the temperature at the top also over here, I think, yes, the temperature at the top here is instead 500, and this one is 100 degrees Celsius. So it is going to be 100, the temperature distribution at node 2 is going to be the temperature 100 to the right, which is this, plus T1, and then plus 500, the temperature at the top, okay, plus again T4, this temperature, minus 42. You understand? So the same thing applies to, if you take, let's say, node 3. In node 3, the neighboring node to node 3 is this node. and then this particular node, and then this node, and then node 1. So it is simply going to give me T4, which is temperature at node 4, plus temperature over here, which is 100 degrees Celsius, plus T1, temperature at top of node 1, node 3, plus again 100 degrees Celsius, which is this temperature over here, minus 43. So the same thing applies to the last one. So this is the fundamental governing equation for what we call central node or interior node. You understand? So now, and the rest is up to you to use matrices to solve this particular equation. But I'm not going to waste my time on this because we will not allow you to use, we will only give you matrices questions when it becomes, let's say, if it is an assignment. Okay, but most cases, we would normally reduce the equation to only 2 or 3 unknowns. Then you can find all other parameters like this. So, and these matrices, I'm going to skip them. They are of no importance. So it is going to be a waste of time for us. Better we should move to a different, what do you call it, question. So, and in relation to the heat transfer, now, let me see, maybe I will discuss this particular one also later on. Let us move on to this particular discussion. So I will come to that particular question later on. Now, for this particular slide, okay, so I deliberately didn't give you any break because I would like to finish quickly, and then so that you will be saving your money, your data. Okay, so bear with me. Just a short slide is remaining. We will finish quickly, and then you can take some rest. Okay, so then next week we will start with chapter 3, inshallah. So now derive the heat equation for node 3 of the plate shown below. Okay, so we have here we have a node over here, node 3. We want to find the heat transfer or the over here. To the right of this node, and then each node, we try to divide them into 2 like this. Okay, we make a division over here. Now, this particular distance, this distance this is delta x, this is delta y divided by 2. You understand me? Similarly, this distance, horizontal distance, is delta x divided by 2. So now, if we want to find a heat transfer with respect to this, now you see over here that we have a certain object over here. This is what we call insulation. Insulation means that there is no heat transfer to the left of node 3. Okay, so insulation is the same as, let's say, adiabatic situation. Adiabatic means there is no heat transfer to the left of node 3. So it's going to remain idle. However, we are going to use what we call mirror image. So mirror image, later on, I'll discuss that. So now let's see the divisions which I have discussed with you is this. So this distance is delta y. So half of it is going to be delta y divided by 2. This distance is delta x divided by 2. So it means the whole of this distance from here up to this portion is delta x. So half of it is going to be delta x divided by 2. So now, in order to determine, since the heat transfer is steady state, then the equation equals to, so delta Q divided by delta T. So now, if we take, let's say, the heat transfer to the right of node, yes, to the right of node 3, that heat transfer is given by Qm plus 1, comma, n. So it means we are considering node 4. If you look over here, this node, this particular node, this node 4. So the heat is transported from this node towards node 3. So now, if we look at the Fourier's law, it is according to the Fourier's times the area. I'll explain this area again. So we know, let's see here, we have the Fourier's law. This equals to K A dt over dx. Okay, so the dx can be the length. You understand? So this K is what we have over here. And the area that corresponds to that heat transfer area is given by delta Y times B. B is the thickness. If you look over here, so try to focus your attention over here. So let's say this is the surface area which is receiving the heat. Okay, so I'm going to shade it. Yes, the surface area. That surface area, this particular thickness is given by B. And then the height is given by delta Y. So the surface area of the heat transfer towards is given by delta Y times B. You understand me? So that's the area. And that's what we have over here. Okay, so delta Y times B. B is the thickness times the temperature difference. So it is going to be T4 minus T3. Okay, so in actual fact, it's supposed to be T3 minus T4, but because of the negative, yes, I forgot the negative sign over here. So because of the negative sign over here, it is going to be T4 minus T3. Okay, so now whichever way you take it, you see that there is heat transfer. There is always the heat transfer is from state 4 towards state 3. So now it becomes T4 minus T3 divided by delta X. And that delta X is this component delta X. Okay, and delta T is simply this. The K is that, the A is that. Now, if we move on to the the top position of node 3, the top portion of node 3. If you go to the top portion of node 3 here, you see, very easy. So try to understand what I'm saying. Here we have, there is heat transfer from this node towards node 3. Okay? But then the heat transfer area, you see this portion, in actual fact, is supposed to extend up to this portion. So that this becomes, the whole of this distance becomes delta X. Delta X. So let me erase this thing. It's now very, it's not so good. Let's see. Let me erase some of the things. Yes, so what I was explaining over here is like this. That if you consider this particular situation where this is node 3, okay, then we have node 1 over here. Now, this distance is supposed to be the whole of this distance from this portion, okay, up to, let's say, up to this portion is supposed to be 1. Okay, so it's supposed to be 1, a magnitude of 1. And then from here also supposed to be magnitude of 1. And then from this top also supposed to be magnitude of 1. But then we normally divide it into half like this, into portions. So we have this. This also will be divided into this 2. This should also be divided into 2 like this. So that this distance becomes delta x. Okay, so this distance becomes delta x. That, I mean, from here up to this portion becomes delta x. And then also, since we divide this also into 2 like this, then this distance becomes also delta y. To understand, that's this distance, that's delta y. Now, of delta x. So it means we are going to consider only delta x divided by 2. You understand? So this area, only this portion we are going to consider as far as the heat transfer is concerned. So we will consider that there is heat transfer from node 1 all the way to node 3, but the surface area that is receiving the heat is this area. Okay, so this is the thickness, this is the thickness B, and this is the length. You understand? So that's the heat transfer area. So now we will have K delta X divided by 2 times B, that's the area, times, again, T1. So wherever the heat is flowing from, the heat is flowing from here, from state 1 up to state 3. So it will be T1 minus T3. You understand? Unlike we have again here, T4 minus T3. So it is going to be T1 minus T3 in this way, divided by delta Y. Why delta Y? Delta, because this is the length. So delta Y is the length across which the heat is flowing. So from here all the way up to node 3. So that corresponds to delta Y. So similarly, we have K delta X times B divided by 2, then T5 divided by, T5 minus T3 divided by delta Y. Okay, so now you see there is one portion which is left behind. That is Q M minus 1. So this Qm minus 1 is the node to the left of node 3. This is supposed to be Qm minus 1, okay, dash N. But we do not consider this one because this one equals to 0 because of the fact that this is an insulation. Okay, the whole of this insulation, so it has no effect on this. So that Q equals to 0. So eventually, if you rearrange this equation, okay, so you can express the temperature and then in terms of each other, the temperature and the nodes. Okay, so that is how to handle this particular situation. Now, if we look into this particular question here, we have a steady state heat conduction in L-shaped block. So now we have insulation over here. Now on top of this section, we have convection. This is a convection situation because air is flowing. Here also air is flowing, air is flowing, air is flowing. And then here we have heat flux onto this particular surface. So the heat transfer coefficient for the individual respective areas are given. You can be asked to determine the steady state heat conduction at node 5 or node 1 or node 2 or node 3. You understand me? So now heat transfer is steady state and 2D. Thermal conductivity is constant, heat generation is constant, radiation heat transfer is negligible. Okay, so now form the volume element by partitioning the region between nodes. Node 5 is the only complete interior node. Okay, consider the volume element represented by node 5 to be full size node. Well, delta S equals to delta Y. And it is true. You see, over here, if I ask you which of the nodes have an interior node is a node in which its neighboring nodes are equally distributed. So the neighboring node of node 5 is node 6. This is node 2. Again, we have node 4 over here to the bottom, and then we have node 11. So this is the only interior node that is complete. But if I consider, let's say, node 4, the only node 4 has, its neighboring node is node 5, and then node 10, and then node 1. But it has no node at the left portion. So this is not an interior node. Node 4 is not an interior node. Similarly, node 3 is also not an interior node because it has only two nodes, two neighboring nodes, node 6 and node 2. You understand? So this is what we call a half node. So I'll come into those cases later on. Okay, so now we will consider, and we have been told that the temperatures T11, T10, T12, all these things are equal to 90 degrees Celsius. Okay, so it means that the temperature at the bottom of the slide, at the bottom of the plate is constant, it does not change. So now if you want to determine the energy balance, okay, and consider node 1. If we have to consider node 1, then we will have a situation like this. So I need to move fast a little bit because time is against us. So if you consider node 1, at node 1, we have its neighboring node is node 4, and then node 2 in this way. I've told you for each particular node, we need to make a clearly distinction by dividing in between this node, we divide it by 2 portions like this, and in between this node, also we divide into 2 portions like this. So there will be a middle portion over here, a middle portion over here. Okay, so if we consider the heat transfer, let's say, yes, so at the top of node 1, again, we have convection situation. So we have to consider the convection part as well. So if you consider the convection first, let's say we start with the convection. So what is the equation for convection? Q convection equals to HA times what? Delta T. HA times delta T. So, and the heat transfer coefficient here is H. And then the area now, the area is equal to this surface area. Okay, so that gives us this particular distance, delta X divided by 2 times the thickness. The thickness is 1. So that's why we didn't bring the 1 over here. So it is H times delta S divided by 2 times the temperature difference. Temperature difference over here, the temperature difference. It is T infinity minus T1. So that's it for this particular equation. Similarly, if you consider the node 2, you observe that there is heat transfer. For node 2, we have heat transfer from, let's see over here. For node 2, we have heat transfer from node 2 up to node 1. But what is the area, the surface area across which the heat is being transported? So the K, there is no doubt, K is always there. So but the area is going to give me this particular distance, which is the vertical distance, half of it. So that's delta Y divided by 2 times the thickness. Thickness is this. So this thickness. Okay. So this thickness is given by 1, a magnitude of 1 times this. Okay. So then it goes all the way up to this portion. Then, so we have delta Y divided by 2 times T2 minus T1, all divided by delta X. Yes, delta X is the thickness across which the heat is flowing. So heat is flowing all the way from left side up to this portion. So the whole of this is delta X. You understand? So like this. So then next we move to node 4. So the same thing. So for node 4, the surface area across which the heat is flowing is this times the, what do you call it? The thickness. Okay. Then the temperature difference, T4 minus T1 divided by delta Y, because we are moving in this direction. then plus G. So now we assume that there is heat generation at Q at state 1. So if there is heat generation, that magnitude of heat generation is this. So now what is going to be the area, sorry, the area across, sorry, the volume of that particular area. So you see, and that over here, let's see equation, the general equation again. If you look over here, this Q is with respect to heat flux per unit volume. You understand me? So whenever you want to determine, let's say, the heat generation at a particular node, say, let's say node 4, node 1, then it should be the heat generation at that particular node, which is G1, times the volume at node 1. Now, how do we determine the volume at node 1? The volume at node 1, I've told you, you have to, again, divide this like this. Okay, so it is going to give us this delta y divided by 2, the delta y divided by 2, and delta x divided by 2 times the thickness. So the thickness is 1. You understand? So this is delta y, sorry, delta x is this, and delta y is this. So that's why we have over here, and by 2 times, or 1 does not affect, and they can simply put all the parameters which are given into the equation, and then we can simplify it into this form. Okay, so the same thing applies to other particular nodes. Okay, so this thing is hanging a little bit. We need to be a bit patient. So we're almost done. Okay, so yes, so like I was telling you, if let's say whilst we are waiting for the computer to reset itself, if let's say we want to find the temperature distribution, okay, for let's say node 2, it is going to be the same, going to have the same situation. So the neighboring node to node 2 is node 5, node 1, and then we have convection at the top of node 2, and then we have heat flux at the right of node 2. You understand? So we need to consider all those things in this way. So let me see what is happening to this laptop. So my system is hanging a little bit. I don't know. We have to be a bit patient. Yes, so please, I'm very sorry for the interruption. My system was hanging. I need to reset it back. So can you hear me, please? Can you hear me? Hello? Salam alaikum.
Yes,
Salam.
yes,
Yes,
Oh,
sir.
okay,
yes,
okay,
yes, sir.
okay. So we are almost done with the slide. Please try to be a bit patient with me. Yes, so like I was telling you, the temperature at this particular node 1, okay, with respect to its energy balance is given by this. So if you substitute all other terms into the equation, then eventually we have this. Okay, so now if you look at node 2, in a similar fashion, in node 2, see this is what we call a half node. So for node 2, you see again, its neighboring node is node 3. To the left is node 1. And then at the bottom is node 5. So this is not a full node. This is what we call a half node. So for each particular node that you consider, you move to its right or the top or whatever it is, you have to divide it by 2 in this way. So the red dotted line is very, very, very important. Okay, so it means in between this node, you give a distance of vertical distance, let's say delta y. And again, in between this node, okay, so then again, this is delta x. Again, this is delta x divided by delta x divided by 2, delta x divided by 2. In other words, from this middle portion up to this middle portion is delta x. And then also from here to that is delta x. So now, similar situation, and delta y. So again, we divide this into 2, then consider this portion. Now, if we consider the convection part, so as far as this fluid is concerned over here, there will be convection on top of node 2. So we need to consider that. But what is its, the convection heat transfer coefficient is H times the area. So now the area is going to give me this distance, delta x times the thickness. So the thickness is this. The thickness is B. So this is the thickness. So the thickness equals to 1. Okay, so we have delta x times 1. That gives us the thickness. Okay, so that gives us the area. So we don't put 1 over here because delta 1 x times 1 is the same. So then times T infinity minus T2. That accounts for the convection part. Now, if we move to node 3, so there is conduction from here up to node 2. But then the area across which the heat is flowing is this distance times the thickness. So the thickness is again equals to 1. Okay, so this gives me delta y divided by 2 times the thickness. So the thickness, which is 1, so that gives me delta y divided by 2 times, again, T3 minus T2 divided by delta x. So delta x, so means this distance, okay? So plus, again, there we can consider that of node 5 also, so which is this. And then finally, the node 1, okay? So the heat transfer from node 1 up to node 2. Plus, if there is heat generation. So here, be careful over here. Yes, how do the student know, say, how to find the heat generation? So the heat generation is per unit volume. You understand? So here we have heat generation. So the heat generation at this particular portion per unit volume. So how do we determine the volume? It is this distance, which is delta x times delta y divided by 2 times the thickness. The thickness. Okay, so the thickness is 1. This thickness equals to 1. So that gives you the volume. Now, next, again, if you substitute all the parameters inside, then eventually the final equation is this. So the same thing applies to node 3. Okay, so the difference between node 3 and all other nodes is that in node 3, we have what we call, yes, so we have the convection also over here. And then I think we have heat flux at the surface of node 3. Let's see. Yes, so that's the heat. Oh, no, sorry. Instead, we have convection on top and convection at the bottom, at the right-hand side of node 3, if you can observe carefully. So we have convection situation here and convection situation here. So we need to consider both convection situation. You understand? So, and this is very important, means we have convection here, convection there. Okay, so for the first portion, we have, you see, by heat convection at the top side, it is going to give us H, which is this H, times the area. So area means this thickness times delta X divided by 2. This is the thickness times this delta X divided by 2. Okay, times 1. So the thickness is 1. This thickness is 1. So now that accounts for this particular one. Then times T infinity, this T infinity minus T3, which is this. So we can do the same thing for the right-hand side of node 3. For the right-hand side of node 3, because there is convection also over here, it is going to be this area. The area is going to give us delta Y, which is this height, divided by 2, times the thickness. Again, the thickness equals to 1. Okay, this thickness equals to 1. So then, again, that is it. So H times delta Y divided by 2. Again, times T infinity. So again, the same T infinity we have over here, minus T3. So it repeats itself. So that's why we factorize T infinity minus T3 out. Then similarly, we have K, that's for the conduction for node 6, and then node 2, and then we have the heat generation. Okay, so eventually the equation reduces to this form. So now there is a method which we call the mirror image. Okay, so then, and if we want to consider node 4, okay, so node 4 is not a full node. So, but in order we can complete it to be a full node because of the fact that this is an insulation material. Okay, we assume that the mirror image of node 5 is given by this. So this means this will be reflected on this particular surface, and that gives us node 5 dash. So then it becomes a complete, if we do that, this node 4 becomes a complete node. It becomes a complete node like this, where the middle portion is node 4, this is node 5, and this node 5 dash is this, and then we have node 1, then we have node 10 at the bottom portion like this. Okay, so whenever you have this situation, then it's very easy. You only need to add the temperature at this particular node, plus the temperature at node 5, plus the temperature at node 10, plus the temperature at node 1, minus 4 times the temperature at node 4. Okay, so then plus the heat generation part. Okay, so the heat generation part times the L. So where L again equals to delta X times delta Y. Okay, so now if we do that for this particular node, so you see we have T5 plus T1 plus T5. Again, the T5 repeats itself because it's the mirror image. And then plus T10, which is this, then minus T4T4, which is the middle portion, then plus the heat generation part. So like this. So, and again, if you consider now node 5 is a simple interior node, so it's just T4 plus T2 plus T6 plus T11 minus T4 minus 4T5, then plus G again times that, and delta Y times delta X, which is L squared. Okay, so, and again, this situation, node 6 is what we call 1/4 node. Okay, so for this particular, is the same application we will use for this particular node. So I'm not going to waste my time on that. If you go through carefully, and this is what we call 3/4 node. 3/4 means this plus that forms a 3/4. And then, and for node 7, so similarly, let's see over here, it is the same thing that I have discussed earlier on. So I'll move on to a very important one. Yes, so this one, node 9. So node 9, that's where we have a heat flux. So if you consider node 9, you see we have what we call convection on top of node 9. Okay, this is what we call actually a quarter node. And then we have heat flux to the right of node 9. So now the convection part is given by this. It is H times the area. Okay, so area is given by delta X divided by 2 times 1. You understand? Then we have times the temperature difference, T infinity minus T9. Then plus Q. So this Q is the heat flux towards node 9. Okay, but what is the area? The area is delta Y, which is this, times the thickness. Thickness is 1. So plus, again, the temperature, again, the heat transfer from node 15, like that. So it goes on and on, then node 8, and then the heat generation part, and so on. Then eventually the equation reduces to this form. So all these equations need to be written one by one, and then eventually either you use simultaneous equation or use matrices to find all those equations. Okay, so I think we have come to the end of the lecture today. Okay, so hope to see you next week, and we will try to see a way in which we can give you some questions and then solution how to solve the questions using either a particular software or tool. So for now, I would like to stop over here. If you have any question, we can discuss. Okay, so